Okay. Page 1, please. Page 1. So we have here this model that you looked at last class that wasn't the test in terms of atoms and particles and molecules. So a couple of things that I hope you picked up from this is that number one, atoms are particles. Yes? Yes. Are molecules particles? Yes, they are. And I'm just going to put up here my abbreviation for molecule, because it's quite a long word and we're going to be writing it a lot. My abbreviation for molecule is MC, like capital M, capital C. Okay? Molecules. So we can then write molecules are particles. And number 3, last but not least, there's actually another type of particle that we learned about in our last unit. Can anyone think of what it is? Actually, there's a few, but I'm looking for one in particular, but you might come up with other options too. Other particles, yes. That's yeah, that would be like many different particles together. Yeah, yeah. You have your subatomic particles, so you have your protons and your neutrons and your electrons. Those are also particles. I'm actually looking for one that is just slightly different from that. I'm looking for a particle that is not a subatomic particle. Can anyone think of something we dealt with in the last unit? Something in the last unit that's not an atom, it's not a molecule, but it's still a particle. And it's not like a subatomic particle. Something else that is also a particle. Atoms are particles, molecules are particles. Ions. Ions are particles. Okay. So if I said to you, how many particles are there in this square here? So if you have an atom, that's a particle. If you have a molecule, that's a particle. When we have a molecule, we don't count the individual atoms within it as particles. Okay, so how many particles are in that yellow square? Tell your partner, how many particles are in that yellow square? How many particles? 8. There are 1, 2, 3 molecules. So we have 3 molecules, and we have, 5 atoms. Now, sorry, 5 atoms. 1, 2, 3, 4, yeah, 5. So how do I know if I have a molecule? Like in these pictures, how do I know? There's 2 or more, yeah? The shapes on it are intersecting. I've got two shapes that are touching. And if those are atoms, then it means that the two atoms have to touch. So a molecule, okay, a molecule is two or more atoms stuck together. So if we look at, now there's another word actually that I want you to think about, and this is one thing that's quite tricky sometimes to distinguish between, is a molecule and a compound. Okay? What is a compound? So let's see what we've got that's a compound here. Is this one a compound? No. Okay. Is this one a compound? Yeah. So what makes, are both of those, are they molecules? Yeah, both of them are molecules, right? I've got a molecule here, right? And I've got a molecule here. One of them is a compound and one of them is not. What makes it a compound, Ethan? Yeah, you have to have two or more different types of atoms stuck together. Yeah, two or more. So if I was to circle this particle here, is that a molecule? Yes, that is a molecule. Is it a compound? Yes, it is a compound. Okay, and let's see, what else have we done here? Oh, yeah. So if SQ2, that's the one that's over here, if SQ2 is not a compound, what is it? If SQ2 is not a compound, what is it? It's a molecule, but it's not a molecule of a compound, it's a molecule of, what do you call it when all the atoms are the same type? Sorry? No, you could be right. Starts with an E. Element. So if all the atoms are the same type, you have an element. Can you find any other elements? Well, let's see. Can you find an element that isn't alone one atom? Yeah, so again, this one up here, the R, okay, that is an element, but they're just circles on their own. And this one over here, what would be the symbol for the one that I'm highlighting now? That symbol, or the code, would be T. Okay, so that's our T. And that is an element. Okay. Are there any more elements in here? We got the circle, that one's an element. We got that one. We got this one over here, that's an element. Now, which of these samples are pure? What does it mean to be pure? RSQ is pure. Pure means all the particles, thank you very much, are the same. So if we look at RSQ, that's the one, let me find a different color here. Down here, one I'm coloring in blue right now, are all the particles the same? I have circle, square. I have circle, square. Yes, they're all the same. They're all circle, square, or round, square. Round, square, round, square, round, square. So that tells me that this sample of matter, is it pure or is it a mixture? It is pure. All the particles are the same. Okay? Is the RSQ a compound or an element? The blue one, the blue sample, I'm going to get rid of these because they're ugly compared with like the actual drawing. Is RSQ a compound or an element? It is a compound because these two are different, yes? And since they are different, that means it's a compound. Now, how about this one that I'm going to color blue right here? Tell your partner as many things as you can about that using all of the words. So you're going to use the word molecule, atom, compound, pure, mixture, any of those things. Hi. Okay, so tell me something about this sample of matter. Yes. It is pure. How do you know that it is pure? Because all of the particles are the same. Therefore, it is pure. Can you tell me something else about it? Yes? It's a compound. Yes. And the particles are molecules. Yes. Now, what would the symbol be? If you look at all the little symbols, those are the things we have up in the top left-hand corner. We've got RSQ, we've got SQ2. Tell your partner what the symbol is going to be for this one here. So, which one, what do you think it's going to be called? Yes. R3 SQ. Yes. What does that little number at the bottom tell you? Yes. Yeah, how many of those are there in the molecule? Yes. It really doesn't matter when we're talking about squares and rounds. When we're dealing with actual elements, there is a reason, and we'll explain that in just a little bit. Okay, so yeah. You mean which letter we put first? Oh, like whether they're upside down or right side up, the molecules? Yes. So if I had instead, let's say I had a square and then I had 2 circles on this side and then one over here, that would be different. Okay, so that gets into something we learn about in grade 11, which is the fact that you can have 2 things with the same chemical formula, but this is what we call its structural formula. The structural formulas can be different. Okay, we're not going to do too much on that this year though. Okay, yeah. All right, so this little number down at the bottom, so let's say we have R3 SQ. This little number, yeah, this tells you how many of that type of atom. In the molecule. Okay. Now this thing here, it is a little number. Below the rest of the writing. Down at the bottom, yes? So it's a little number down below the rest of the writing. Do you guys know a prefix that means below? Below. Sub. And if you were to write a play, what would you call that? If you wrote a play, you have written a script. Yes, a play has a script. Script simply means writing, okay? That's why a play's script is called the script. And that's why you have a prescription. It's something that the doctor writes for you, that script in the middle, okay? So we have a thing that is below the writing, and so that little number there is called the subscript. Let's see if I've missed anything here. Nope, I haven't. I don't think. Just to point out, when you have a chemical bond, when drawing the molecule, the atoms must be touching. Okay? Now, what if I was to ask you, and what if we went back up here, okay, and we looked again at this TRSQ plus R, what would we call that entire sample of matter? What would we call that entire sample of matter? I have some molecules, I have 3 molecules, and I have 5 atoms. Yes, this is a mixture. And if you don't have any room, you can write it like up in here, mixture. Yeah, that's a mixture. Do you remember the 2 types of mixtures that you learned about in the homework? Homogeneous and heterogeneous. And if you have problems remembering how to say it, it's like the word genius, like super smart, right? And so you're going to either say homogeneous or you're going to say heterogeneous. Okay. Is this mixture, what do you think? Is this mixture homogeneous or is it heterogeneous? Tell your partner what you think. And I will be fair with you. I will be completely honest. A sample size this small, sometimes it's hard to tell. Yes, it's easier when you have more particles shown to tell. Yes. Yeah. Hetero? Why do you say heterogeneous? Okay, why not? Fair enough. Okay. Anyone want to make a guesses and a reason? Yes? Yeah. Uh-huh. Okay. Now, one thing I'm going to say, and this is exactly why I would never give you this one on a test, because it is such a small sample. It might look like you have kind of a clump, but like the triangles are not clumped together, right? They're not clumped. We do not have a clump of circles, nor do we really have a clump of the molecules. So my best guess on this one would be that it would be homogeneous, but it's not a really good example, okay? Because it's such a small amount. It's hard to say, ooh, I have a clump of 3 particles. That's not really big enough to almost be a clump. You know what I mean? Yes. Yeah, yeah. So let's just write a couple things down. So we have types of mixtures. So you can either do this on a piece of paper, or some people wrote it on their inside cover of their book, whatever you like. There's paper at the back if you want to take a minute and get some. Help yourself. Paper. You want some paper to write on. There is no page. We're just writing on paper. If you need paper, there's some at the back. Then you're good. What does the prefix homo mean? It means the same, okay? Okay, so homogeneous, it appears the same throughout. If you have salt water, which is a homogeneous mixture, can you find different areas of the salt water that look different from one another? No, all the salt water looks the same. All the properties are the same throughout. So for example, our salt water it's all clear, it's all colorless, it all tastes salty. There's no differences. Yes? So that's from homo, which means the same. And does that make sense with where we've heard that prefix before? In homosexual, those are people who are attracted to the same sex, yes? Whereas heterosexual, hetero simply means different, yes? So heterogeneous and hetero means different. And actually these prefixes will come up again if we get that far in our biology unit. You can have two chromosomes. You know how you get two chromosomes, you get one set of chromosomes from your mom and one set of chromosomes from your dad. That's like your genetic material. Okay, and you get one set from mom and one set from dad, but they're like a matching set. Yes? So if you got a chromosome from mom, it's gonna have like eye color, hair color, maybe on one chromosome. Okay? The one from your dad will also have eye color and hair color. Now, if you have brown eyes from mom and brown eyes from dad, like the gene for brown eyes from both parents, we say that that is homozygous. Okay, homozygous, which is going to come up again. Remember, homo means the same. So it means you got the same color gene for eye color from both mom and dad. But if you got a brown color from dad gene and you got a blue color from mom gene, then you would be heterozygous because you would have a different color gene from each parent. You got a question? No. Okay. All right, so hetero means different. And what it means is that different areas have different properties. And this is due to the fact that you have little clumps of, you can have little or big, clumps of a particular type of matter. So let's say that you had some water and it's muddy water. Have you ever looked at muddy water up close? There's like little clumps, yes, of dirt. And eventually those little clumps of dirt, if you leave it long enough, what will happen to them? They'll actually settle down to the bottom, okay? So there's little clumps of dirt suspended in the water. Suspended in the water. So you have little clumps of dirt and then you've got water. Yes? Eventually, the dirt will settle to the bottom. So you have two different areas. You have the dirt area and you have the water area. Even when they're really small clumps, it's still a different area. Yes, of course. And therefore this is heterogeneous. And we're going to do one last thing before I send you on your break. Sorry. We good? No? Okay. It's okay. Let me know when you're done. Take your time. There's no rush. We good? Okay. So one last thing before we go on break. You are going to, knowing that at the particle level, So that's like zoomed in trillions of times. Yes? So zoomed in trillions of times. In a homogeneous mixture, what can you say about the particles? Yes. Multiple of the same particles? Well, yeah, there's always going to be, anytime you have any sample of matter, you're going to have multiple of the same particles. You'll see multiple types of particles at the same time. Also, yes, they're spread evenly. The particles are all spread evenly amongst each other. So maybe I should say different particles are all spread evenly amongst each other. And if it is heterogeneous, what will you see? You'll see little clumps. You'll see clumps of the same type of particle. So what I'm going to get you to do is I'm going to get you to draw a homogeneous and a heterogeneous mixture, and you're going to use particles that look like, you can use other ones as well, but a simple one would be like where you have like black circles and white circles. You could use squares if you want to. So you're going to draw one little box that contains a homogeneous mixture and one little box that contains a heterogeneous mixture. And you're going to show it to me, and once you have shown it to me and I'm like, yes, it's good, then you can go on break. Okay? Yes, I can go up. In fact, I can do that. How's that? Yeah? Page 5. Yep, I will. So what you're going to do is you are going to consider these options here, all right? And with your partner, you're going to discuss what you think, which material is the odd one out. So you're going to think about it, and then we are going to vote. Okay, so think about it, the odd one out, the one that doesn't match the rest. Okay? There's only one in each group of 4 that doesn't match the rest. So you're going to do that for group 1, and then the group in group 2, and then 3, and then 4. So discuss with your partner or whoever you are near. Do you want to go sit over by Wilfred today so you have someone to talk to? Or is Alex coming back? Where's Alex? Yeah, so it's like these ones here. Which one of those is the odd one out? Okay. Which one of those is the odd one out? And then if you got number 1, try thinking about 2, and then number 3, and then number 4. Well, the odd one out means the one that doesn't match the rest. All right. So we're going to vote by using sign language. So just to remind you, the letter A, you take your fingers and you put them on your palm flat, and then you put your thumb beside it. That is an A. That's an A. No, I'm just showing you where your fingers go, okay? That's an A. B, your palm is like that, and you put your thumb on your palm. Okay, so fingers together, thumb on your palm. That's a B. C is really easy. Okay, C is really easy. And then D, you point your pointer finger up, and then the rest of your fingers and your thumb make a circle. Okay, so like that. Okay, that's a D. Okay, so pointer finger up and the rest of your fingers make a circle. Yeah, yeah. Okay, so let's try those again. A, B, C, and D. Okay, so we're going to do it a few times. A, B, C, D. Should we do it again slower? A, B, C, D. And one more time. A, B, C, D. All right. All right, so which one would you like? Would you like A, B, C, or D for the odd one out in group number 1? 5, 4, 3, 2, vote. Okay, I got some C's. I don't know what that is. I got a D. Okay, so I've got an A, or sorry, I've got some C's and some D's. All right, so let's think about this. What is the symbol for copper? Cu. Yes? What is the symbol for gold? Au. And if you don't know that, one way of remembering it is if somebody comes along and steals your gold watch, you go, AU, that's my watch. AU, that's my gold watch. Now, salt, this is table salt. And it is actually sodium chloride. Do you know the formula for sodium chloride? What's the formula for sodium? Na. And this is a compound, so it is bonded together with the Cl, and so we write those two touching each other, okay, all in one word, as it were. Okay, yes? You don't need a mass number because you're dealing with an entire sample of matter, so you'll have all sorts of different isotopes in your sample. Yeah? Yes, sodium is an ion and chloride is an ion, and we'll be looking at how that forms a little bit later today. And then finally, the formula for sulfur is S. So what can you say about A, B, and D? What do they all have in common? They are all elements. Okay, so we have an element, we have an element, we have an element. And what is salt? Salt is it's a combination. So therefore, it is a compound. And remember, a compound is made of two or more elements stuck together. Two or more different. Okay, in our second group, we have rust, we have silver, water, and wood. You are going to vote for me which one is the odd one out. In 5, 4, oh, do you want to remember again? A goes like this. B, C, D, B. Okay, so A, B, C, D. Do it with me 10 times. A, B, C, D, 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 A, B, C, D. I'm not very good at it, but I have done it for like many, many years, just not often during those 20 years. My friend and I learned sign language when we were in grade 12 because she had a spare at the same time as I had a class, and we wanted to be able to talk to each other if she was in the hallway. So, alrighty. So which one is the odd one out? 5, 4, 3, 2, go. Well, I don't know what that is. This is the letter O. There is no O. In fact, that's not an O. This is an O. Are you doing a B or are you raising your hand? You're raising your hand, yes. You can go fill up your water, yes. Okay, I got some C's and I have some B's and I have an A. Okay, let's make this a little easier for you. We're going to give you the formulas. Rust is iron oxide, Fe2O3. No, you don't need to know them, but is our next unit all about writing the names and formulas, so it would behoove you to pay attention? Yes. I usually don't do things without having some end goal in mind. Yes? Fe2O3 is iron oxide. Silver, what's the symbol for silver? Ag. And what is the symbol for water? H2O. Now, wood is based upon carbon. Carbon compounds are really complicated, okay? They can have really long formulas, but they all involve carbon, some amount of carbon, so I'm going to call it CX, because we don't know exactly how many, okay? H, they involve hydrogen, and again, we don't know how many, so I'm going to call that Y. And then they also involve oxygen. We don't know how many, so I'm going to call that Z. Okay? It's complicated. So what can you say about A, C, and D A, C, and D are all compounds. Okay, so we have a compound, we have a compound, we have a compound, and silver is an element. Yes. Next one. Which one is the odd one out? 5, 4, 3, 2, go. Yes, it is C. What is the symbol for helium? He. Oxygen, O, and in fact, when it is found in nature, it is actually O2, which means that instead of it being single atoms, what is oxygen like? Oxygen has 2 atoms bonded together. Yes? 2. Plastic is another one of these organic compounds, a carbon-based compound. It's another one of these really weird C something, H something, O something else. It's complicated. Yes? And then potassium, of course. Do you guys know the symbol for potassium? K. So what do A, B, and D all have in common? A, B, and D are all elements. And C, on the other hand, is a compound. In our final group, we have, for your science enjoyment, sand, carbon, bromine, and magnesium. Which is the odd one out? 5, 4, 3, 2, go. It is. You do like the weirdest symbols. Like, this is not a sign. Okay, it is A. Okay. A, yes, sand. Sand is actually made of silicon and oxygen. Silicon dioxide, that's called. Okay, carbon, of course, is C. Bromine is another one that is a Br2. And magnesium is Mg. You're actually going to learn all of the elements that have like a little 2 at the bottom. We will learn those ones a little bit later, okay? Now, I think I had meant this to be like a fill in the blanks, but I forgot to remove like the filled in part. So we're just going to highlight things or, you know, just read along with me. If you would like a highlighter though, and you would like to borrow one, I do have some here. So feel free to take a moment, get yourself a highlighter if you want to highlight along, okay? If you have your own highlighter, that's good too, but I do have spares for loaning. Oh, for goodness sake. Okay. So there are so many different types of materials in the world, but there are only around 100 elements. It's getting closer to 120 now, but that's correct. However, you can combine these elements in order to make, I would say, maybe not even thousands. I would say we are probably more in the millions of different compounds because the combinations are almost endless, okay? So if you have an element, all the atoms are of one type, okay? In an element, you only have one type of atom. So if we look at our picture of the copper, this is like a copper basin. These are all copper molecules. These are all the same, all copper atoms. This is not a particularly good picture. They're supposed to be little black circles. Carbon is made, and this would be like charcoal, or it could be like the graphite in your pencil is also made of carbon. These are all the same. They're all carbon atoms. Helium is made of only helium atoms. And then we're going to draw one more balloon. Because maybe in our balloon, we have bromine. And bromine is made only of Br2 molecules. So that's an element as well. Yes. Because on the periodic table, we're just looking at like the substance, not in any particular form, like it could be combined with another. We're just using it to say either it can be combined with itself or it could be combined with another element. It's sort of the most basic form of it possible. It's not that you cannot get a bromine atom, it's just that if there are two bromine atoms in proximity to each other, close to one another, they will get together and they will bond, given the alternative, okay? All right. So, molecules of elements. Atoms of some elements join together, and the word for join together is bond. And when they join together, they make molecules. One of the elements that exists like this is hydrogen. Ethan and Terrell, why don't you guys come sit up here? Yeah? Each hydrogen atom joins up with another hydrogen atom to make a hydrogen molecule. So you can see we've got an atom and we have a molecule. What would the formula for the hydrogen atom be? Formula for the hydrogen atom is H. Formula for the hydrogen molecule is H2. Yes. I'll give you guys a minute to move. Yeah, it's totally fine. So, formula for the hydrogen molecule is H2. It is a molecule. It is made of two atoms. The prefix di means two. So we can say that this is a diatomic molecule, meaning that we have two atoms. Bi is a different, we just don't use that in this context, okay? Now, you can, but not here, okay? In science, we mostly use di for two, okay? Other elements, such as nitrogen, oxygen, and chlorine, are also diatomic, okay? So you can see we have N2, we have O2, we have Cl2, okay? So when they're just hanging out in nature, they are N2, O2, and Cl2. Yes? Pardon me? Yes, tri for 3 and tetra for 4. Often once we get past 3, we will simply say poly for many, but we will do, there is a little bit of a unit in the naming where we do like tri, tetra, penta, hexa, hepta, octa, nona, and deca. We go up to 10, okay? How would we draw a molecule of Cl2? What would it look like? Two Cl's together, so we would draw one atom, Cl, and where would we have to put the other atom? right beside, sticking to it, Cl. Okay? And this is a molecule that is bonded together covalently. And what that means, and we will talk about this a lot more later on, but when things are bonded covalently, it means they share electrons. Okay, so don't worry about it too much for now, but this will come up later, so you might as well hear the word now. So this is a molecule of an element. However, not all molecules are elements. Can you think of a molecule that is not an element? H2O, because we've got two different types of atoms, okay? So when we have two different elements that are bonded together, then we get not an element, but a compound. We have combined NaCl is a compound, yes. We have combined two or more elements, and that is a compound, okay? So you can see here what we've got is we have hydrogen. How many hydrogen molecules do we have? We have 2 hydrogen molecules. So I could actually write it like this. This is what you'll be doing in grade 10. Just to give you a tiny preview, this is not for this year, but you would say I have 2 H2 molecules. And to that, I'm going to add, how many O2 molecules do I have? I have 1 O2, so I'm just going to write O2, and I don't have to put a 1 in front of it. And then when I have the arrow, what that means is that they react to form. So if I take hydrogen and I put it together with oxygen, they will react to form how many water molecules? 2 waters. So you're going to have a ratio of 2 to 1 to 2 for the number of molecules in there. Why do I need to have 2 hydrogen molecules for every 1 oxygen molecule? To make water. Yeah. Yeah. That's a good guess. But if we look at our oxygen, how many water molecules can we make with 2 oxygen atoms? How many can we make? 2, right? Because you can make 1 with one and 1 with the other. And how many hydrogens does that need? It needs, every oxygen needs 2 hydrogens, right? And so that means that you're going to end up with 4 hydrogen atoms over here and 4 hydrogen atoms over here. The number of atoms remains the same from side to side. That's going to be important in grade 10. Don't worry about it for this year very much. Okay, we're more focused on just the formulas. What kind of a process is this? Is this a chemical change or is this a physical change? Okay, here's a good clue. When these two things react, what has to happen is that these bonds have to break. Those 2 hydrogen atoms have to separate from one another, yes? So the bonds break. What has to happen with my 2 oxygen atoms that are right now stuck together? That bond has to break because they're no longer attached over here, right? The oxygens are not attached to each other. So this bond has to break. And there is a bond here and a bond here. Were those bonds there before? No, those are new bonds that have to form. So new bonds form. Yeah. When old bonds break and new bonds form, we have a chemical change. We have had a rearrangement of the atoms in those particles, yes? We started out with an H together with an H, and now the two H's are together with an oxygen, okay? So, moral of the story, a compound has two or more different, I could have circled that better, couldn't I? Different elements bonded together. And that's why water is a compound, but hydrogen and oxygen are not compounds. Yes? Sorry? Yeah. You would take some hydrogen gas and you would take some oxygen gas and you would set a spark to it. Bang, it goes, and you will get water. You can, I mean, there are like local gas companies that will like give you hydrogen and oxygen gas. Probably next week, I think during the long block, I'm gonna generate some hydrogen gas with you guys, and then we're gonna put it into a balloon, and then we're gonna make the balloon go, bang. Yeah, yeah. Yeah. Yeah, okay. If it wasn't report card week, we might have done it this week, but I was just too exhausted with everything that's been going on. I'm like, I can't, like, the thought of putting together a lab and a demo, I'm like, I can't, I'm just, blah. Yes, that's water. Yes. It would actually be fairly pure. Yes, because it wouldn't have anything dissolved in it yet. So anytime you have like tap water, there's little bits of stuff dissolved in it. There's a few little minerals and whatever. We could make high quality water. Of course, if you blow up the balloon, there's also your spit in there, but you know, yeah. Okay. Now, molecules of compounds. Covalent compounds. Covalent compounds, those are where electrons are shared. They are made exclusively of nonmetals. So if you have a metal and a nonmetal, you cannot make a covalent compound, okay? And the reason is that metals really like giving electrons away. Non-metals really like taking electrons. So if you put two non-metals together, they're both trying to take the electrons, so they end up just sharing them because they're both pulling on them about equally. However, if you put a metal with a non-metal, if the metal likes giving them away and the non-metal likes taking the electrons, then who's going to end up with the electron? Metal likes giving them away, non-metal likes taking. The non-metal is going to end up with the electron. It's going to become an ion, so that electron is not shared. Okay? So here we go. Here are a couple of molecules of compounds. What is the formula for water? H2O. Is it like this? Is it like this? Or is it like this? Yes. Because, of course, what do we call that little number at the bottom? It is called a subscript, and the subscripts have to go below the writing, okay? Carbon dioxide, made of 1 carbon and 2 oxygens. What is the formula for carbon dioxide? CO2. And now for something completely different. This is a crystal lattice, okay? This is what ionic compounds do, and ionic compounds are between metals and nonmetals. So ionic compounds are between metal and nonmetal. And as the name says, they are made of what type of particle? Ionic compounds are made from ions. Metal and non, but you're right, metal and non-metal, but they're made from ions because they're ionic compounds, yes? So made from metals plus nonmetals. And if we have sodium, what group is sodium in? It's in the first one. So how many valence electrons does sodium have? It has 1. So what does it want to do with that electron? It wants to get rid of it, yes? When it gets rid of it, what's its charge? Na plus. So we've got Na, which is positive, yes? Cl, what group is Cl in? It's second from the right though, right? That's group 17. How many valence electrons in group 17? 7. So what does chlorine want to do? It wants to gain an electron. So what will its charge be? -1. So we've got sodium, which is positive, and chloride, which is negative. What do positive and negative do? They attract. So they're going to be pulling towards each other. And you can actually see in this crystal, they are all stuck together. And they're not stuck together like sodium, sodium, sodium beside sodium, because positive and positive would repel. Can you see how they're all like alternating? Sodium, silver, chloride, green. Sodium, silver, chloride, green. Sodium, silver, chloride, green. Yeah? Yeah? And it does that in 3 dimensions. Yes? And so if you have a really big salt crystal, you would have something that's way more massive than this. You just have more of it going along. And if you have a really small crystal, you would just have a smaller arrangement of this 3D crystal. Yes? No, not really. Okay. However, some ions do. Okay. Yeah. Actually, that's not true. Some of the atoms, if they're together, they will have colors. So, for example, gold is gold, copper is copper, bromine, well, that's diatomic. Sulfur is yellow. You know. Yeah. Okay. So this is what we call a crystal lattice. It is really hard to draw this, yes, because 3D is really hard to draw. So often we will draw it in 2 dimensions, and in between the positive and the negative, we have an attractive force. What do you think we call that attractive force between the positive ion and the negative ion? It's an ionic bond. Okay, so that attractive force is an ionic compound. Sorry, an ionic bond. That's what I'm trying to say. Have any of you ever had a pie with a lattice crust on it? Okay, if you've ever had a pie where, you know, you have like strips of dough across the top and it goes like this, and then you have the other strips of dough and they go like this, that's called a lattice crust. So that's where the term lattice comes from. It's sort of this like regular arrangement. Yeah? Okay, maybe that doesn't help. That's all right. Now, if I have this crystal right here, how many ions are in that? Well, we can kind of make an approximation, yes? Or actually, we can count them. Across here, we have 1, 2, 3, 4, 5, 6. So I have 6 by 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6, 7. So that's 6 by 6 by 7. So if I say how many particles are in there all together, I can't do that math in my head. Yeah, what is that? 6 times 6 times 7. Yeah? It is 252 because I used my calculator. Okay, because I can't do it in my head that quickly. Okay. Yeah, so you would have 252, or you would have 100, and so half of that is 126 sodiums and 126 chlorides. So can you imagine if we had to write the formula like this? Na 126, Cl 126. Does that seem reasonable? No, it's really not reasonable. And what if you have a bigger crystal? What if you had a crystal that was twice that big? You could have Na 252, Cl 252, but your crystal could be any size. You can have big crystals, small crystals, medium crystals, they're all different. So it doesn't really make any sense to write in actual numbers. So what we do is instead we simplify it to the smallest ratio. How many sodiums are there for every chloride? If you have 1 sodium, how many chlorides? 1 chloride. So for the formula, we simply write NaCl, which represents a 1-to-1 ratio, rather than trying to make like a formula for every individual crystal. Yeah? So when we write the formula for an ionic compound, what we're really doing is we're making the smallest ratio between the ions. So there is 1 sodium ion for every 1 chloride ion, and so the formula is NaCl. They can kind of do some stuff with like X-ray crystallography, but I don't know. Yeah, I feel like that's too complicated. Mixture versus compound. Mixture versus compound. What is the difference between our mixture and our compound? Take a look at those two pictures. Tell your partner what makes it one of them a mixture and one of them a compound. We will have working time, but we need to get through this first. Yes. Yes. Well, I'm not going to tell you that right this second because I need you to answer this first. So how do we know this is a mixture? Yes. You're on the right track. How do we know that this one on the left, this one here, how do we know that this is a mixture? They aren't bonded together. What we've got is we've got different types of particles. Yes? Yeah. Okay, so we have different types of particles. We have O2 molecules, and we have H2 molecules. So that's what makes it a mixture. We're gonna get through what we get through. We're getting through it as fast as we can get through. I just need to get to the same place as our other block, okay? Compound. How's this compound looking? How do we know it's a compound? Yeah, the H is bonded to the O. Are compounds pure substances? Are compounds pure? Tell me about all the particles in this sample of matter. All the particles are H2O. Yes, and since all the particles are the same, yeah, then yes, it is pure. Okay, since all the particles are the same, that is pure. So when you have a mixture, you have different particles. When you have a pure substance, they're all the same particles, even though within that compound, each molecule has different atoms, but every single molecule is the same as every other molecule. So question, why is it safe to put sodium chloride on fish and chips, but it is not safe to use sodium and chlorine? That's okay. Maybe I feel like it's because sodium chloride is NaCl. It is a compound. It's made of two different things. Whereas sodium and Cl, and Cl is one of our diatomic ones, so it's Cl2. They're different substances, yes? Well, that's because somebody put salt on it. Yeah. Uh-huh. So sodium chloride is a different substance than sodium and chlorine, and different substances have different properties. So for example, the property of sodium chloride is that it tastes like salt. Yum. Now, if you were to put sodium and chlorine together in the same space, it would literally explode because those two things are very reactive with each other. Yes. That's right. That's right. Because when they're in their sodium and chlorine form, the sodium is like desperate to get that electron gone. It wants that electron gone from its outer shell. And who is it desperate to give it to? It's desperate to give it to chlorine. Whereas once they have got that full outer shell arrangement, they are now full and satisfied and stable. And now they just hang out and taste nice and salty on your chips. Chlorine is what we put into pools, yes. Yeah. Like there? That's actually a good thing. Salt is not particularly good for you. I mean, you need a little bit of salt, but you will get whatever you need just from eating like normal food, like an apple and spinach and whatever. There's little tiny bits of salt in there, and you get all that you need from that. Yes. It would explode, yes. And I'm not quite sure where my large sample of sodium has gotten to, but look what I got. I got some little elemental lithium and sodium and potassium, so we might have to try that out. Okay? Again, next week, because this week I can't wrap my head around it. Okay, so your homework. It's not a lot. You've got 4 days, right? Yeah. No. You got to be on the ferry. You know what? On the ferry, just do a little homework. Get it done on the ferry. Yeah. Okay, so we have pages 9 to 12 and hold on. You are also going to do page 21, 22. We are going to, in the last 7 minutes of class, watch the video with Tyler. Okay, so you can do pages 21 and 22. And then the third thing is you are going to do page 23, 24. You're going to watch the video and answer the questions. It really isn't very much. Probably less. I know, right? I know. So you guys are going to work on pages 9 through 12 right now. If you need to go out and run around in the sunshine to feel a little bit better before you start that, that would be a good idea. Okay? You look like you're dying there, Ethan. There's no school on Friday, no school on Monday. Yes. Uh-huh. Let me go through my stack of element activities are, that looks promising. Look at your eyes. Watch out, there's glassware behind you. Perhaps, you know what? You could go outside and continue your wrestling match.